We're going to finish off Le Chatelier's principle with calculating the impact of changing concentrations. I've been having you do this qualitatively, but now we're going to go through some calculations. So first, let's consider the famous Haber process here. Nitrogen plus 3 moles of hydrogen makes 2 moles of ammonia, and we're doing this in a closed 2-liter flask. The first thing is to write the equilibrium expression, and in this case, we're going to use Kc. So we should be able to rather quickly write down that Kc is the ammonium concentration squared over the nitrogen concentration multiplied by the hydrogen ion concentration, all cubed. So here is the question. What is the value for K? And we're given some equilibrium concentrations here. If N is 0.399, hydrogen is 1.197, and ammonia is 0.202 at equilibrium. So I want you to go ahead and solve for that, just for a little practice. And you should have set up your equation as I have shown here, 0.202 squared over 0.399 multiplied by 1.197 cubed, and you get 5.96 times 10 to the negative second. Now, what we're going to do is we're going to increase the nitrogen to 1.399 molar. So we've taken our nitrogen and we have increased it. We're going to calculate Q and determine which way the reaction will shift based on the value of Q. And it should jive with what qualitatively you would predict. And so we'll talk about that after you do the calculation. So now I want you to calculate Q. So pause and calculate Q. So there is the calculation. You should have calculated that QC is 1.70 times 10 to the negative 2. If we compare those, we can see that QC is greater than KC. Remember, if Q is greater than K, that means, excuse me, I've got the wrong way around. Q is less than K. Let's scribble that out. Q is less than K. Since Q is less than K, the reaction has got to shift forward. What we have right now is too many reactants, so our numerator is too small compared to our denominator. So the reaction will shift forwards until Q equals K. Now, this is exactly what you would have predicted looking at the reaction up above. So we increase the nitrogen. I'm drawing a little arrow up here. So we would expect that our reaction would shift forward to consume the nitrogen. At the same time as that happens, our hydrogen is going to decrease in concentration because it is reacting with the nitrogen, and our amount of ammonia is going to increase. I'm going to circle our initial change. So Q is another way of establishing what is going on. Let's take a look at changing container volume. So we looked at calculating the impact of changing concentration. Now we're going to look at the impact of changing container volume. And we're going to look at the exact same exciting reaction. Okay, so we've got nitrogen reacting with hydrogen to form 2 moles of ammonia in a closed 2-liter flask. And we're given the partial pressure of NH3, partial pressure of nitrogen, and the partial pressure of hydrogen at equilibrium. So once again, we are going to calculate the value of K. So we would write that Kp is equal to P squared NH3, partial pressure squared, the partial pressure of N2 times the partial pressure of hydrogen cubed. So that is going to be 10 squared over 1 times 2 cubed, which is 12.5. Now what you're going to do is calculate the partial pressures of nitrogen, hydrogen and ammonia if the flask volume is decreased from 2 to 1 liters. So let's see what's going on. The partial pressure of NH3 is currently at 10 atmospheres. So I'm going to put everything we're starting with. And the partial pressure of the nitrogen is at 1 atmosphere. And the partial pressure of the hydrogen is at 2 atmospheres. And we're decreasing the flask volume from 2 to 1 liters. Now, I want to refresh your memory on something. Remember that P1 V1 equals P2 V2, if you're wondering out how to do this. So what we said was we went from, so we have P1 at a volume of 2 is going to be equal to P2 times a volume of 1. And that means that our pressure will double, okay? So we're going to go to 20 atmospheres. We're going to go to 2 atmospheres. And we're going to go to 4 atmospheres. So when we change the volume, what we are doing is changing the partial pressures of the gases that are involved in the equilibrium. So the pressure doubles. As volume is halved. A little bit of review from your gas laws. Okay, now you're going to calculate Q with the new values and determine which way the reaction will shift. So let's do this. So now Q is going to be equal to 20 squared instead of 10 squared, 2 instead of 1, and 4 cubed. Now we have a value of 3.13 compared to 12.5, which we calculated earlier. Q is less than K. So the reaction shifts forward. I'm going to abbreviate that. Shifts forward until Q equals K. So Q less than K, the reaction shifts forward until Q equals K. All right, let's go back and do this how we were trained to do it earlier, where we just did this qualitatively. So we decreased the volume, which means we want to move to the side of the fewer moles of gas, which is the ammonia side. Fewer moles of gas. And that's exactly what Q also told us to do. So the math backs up our qualitative solutions. Now let's do one more. We're going to calculate Q if we add 3 atmospheres of inert argon gas to the original flask. So let's refresh your memory. Write this reaction down here. We have N2 plus 3H2 is in equilibrium with 2NH3. And we write the equilibrium expression, and it's a Kp. We have P, NH3 squared, over P, partial pressure of nitrogen, partial pressure of hydrogen, cubed. Do you see argon gas anywhere in there? There is no argon gas. So Q is still going to be equal to K after adding argon, because argon is not part of the equilibrium expression. Argon is not involved in the equilibrium. It won't react with anything. We don't care. So inert gases or substances do not impact equilibria. So inert gases or substances do not impact equilibria. All right, now we got a big one. So far what we've done with Q has backed up with what you've learned how to do previously. If you add reactant, you know the reaction's going to shift away from the reactant. If you decrease the volume, you know the reaction will shift to fewer moles of gas. But what happens if we change two things simultaneously? How do we handle that? Well, this is what the next equation is going to do. We're going to use Q to set up a Rice table appropriately. So consider the reaction carbon monoxide reacting with H2O to form CO2 and H2, and we're given a K of 5.10 at 700 K. 1 mole of each component is mixed in a 1-liter flask. Calculate the equilibrium concentration of all the components. Well, you know what? I'm just going to go ahead and fill this in part first. So I have 1, 1, 1, and 1. All right. So the question is, which way is the equilibrium going to shift? How do I know what's a plus X and what's a minus X? So what we're going to do is we're going to compare Q to K. So we know which way the equilibrium shifts. So Q is equal to CO2 times H2, products over reactants, carbon monoxide, and water. And fortunately, we chose 1 for all of these values for the sake of demonstration to make life easier for you. So that's 1. Q is less than K, which means that we need more product. To reach equilibrium. So we need to get to that value again of 5.10. So if we know we need more product, that means that we have to add H2 and we have to add CO2. And we have to lose H2O and lose carbon monoxide. So we end up with 1 minus X, 1 minus X, 1 plus X, and 1 plus X. Without being able to compare Q to K, we would not know how we need to change these X values. So now we can set up our equilibrium equation where we would have K is equal to 5.10, which is going to be equal to 1 plus X squared, because we have 2 of these, over 1 minus X squared. Okay, if you were doing this for an AP grader or me on a written exam, this would be your minimum shown work. Some of you will get to the point where you won't need to do the ICE table, but you still need to show this as a minimum. And then we've got perfect squares on both sides. So we take 5.10 square root is equal to 1 plus X over 1 minus X. And I leave you to finish that one up on your own. So key point here is that if we start off with all of the concentrations provided and we know we're not at equilibrium, we're going to have to calculate Q to figure out whether we're going to be subtracting X or adding X in which columns.